SwayamPrabha. Digital India. Educated India.
Okay, so we started talking about vortex induced instability as computed, and this was a kind of a typical set of results shown for a computation done in a domain like this. So, what you have basically is a sharp leading edge flat plate. The flow is coming at a 0 angle of attack, and then over and above this computational domain, you have a discrete vortex that could be viscous or inviscid, does not matter, that is convecting very far up. The instantaneous location of this vortex is indicated by an arrow like this. As you can notice, there is an arrow here, 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 and so on and so forth. This top 3 frames shows you the streamline contours for a flow field, for which the calculation is started when this is far upstream of the computational domain. And then as we go along, for example, this result is shown as t equal to 62. The vortex is now in our field of view inside the range of the computational domain given by this arrow. So, what you see as the effect of this, there is a kind of a thickening of the shear layer, and this is exactly what we said, that if that vortex is a counterclockwise one, then it will try to scour it out. So, that scouring effect you can basically see leads to thickening of the shear layer. If you look at it a little later time, so this was t equal to 62, this is t equal to 82. Now, you can see actually what has happened. This scouring leads to a bubble formation, and this, since the cause is moving, the resultant bubble also moves, and that unsteady separation bubble, as it moves, what it does? It creates a altered pressure gradient around itself, isn't it? So, think of the following, that if you are having a flow like this, quiescent flow, well, the streamlines are somewhat like this. It just simply diverges because of the thickening of the boundary layer. Now, if I create a separation bubble like this, then what happens? Locally on this side, I am going to create a strong adverse pressure gradient, and that adverse pressure gradient will further destabilize. So, if this is a result due to a primary instability, then the primary instability itself will cause adverse pressure gradient ahead of it, that would lead to the secondary and tertiary and so on and so forth. And you can see what really has happened. As we seen in our analysis in the last class, that a single convecting vortex creates a adverse pressure gradient ahead of it, that leads to a major primary bubble forming, and you can see the distance of separation, it is quite ahead, but then that itself creates a secondary and tertiary instabilities ahead of it, and this movement actually is very pronounced. So, what happens is, once the primary bubble starts, you actually switch on a cascade process. This leads to a sequence of instabilities, and this is what is seen in these kind of dark blue shade, indicating locations of secondary and tertiary bubbles forming. And if you look at little further later time at t equal to 90, you can see the primary bubble has not moved very much, but look at the speed at which the secondary and the tertiary events have occurred. And you can also notice the edge of the shear layer, which is given by the edge of this blue line. You can see these are sort of lifted up, or we call this as kind of a vertical eruptions. So, these individual bubbles indicate lumped vortices. This lumped vortices, as they all move downstream, they are also kicked up, and these vertical eruptions are a very trademark signature of even fully developed turbulent flow. We will talk about turbulent flow as we go along. You will see that even there, each cycle of turbulence, you have various stages of flow development. One of the stages is called the ejection stage, and during the ejection stage you do see such vertical eruptions. So, basically through this controlled numerical experiment, you can pick up those basic prototypical modules which you expect to see even for fully developed turbulent flow. So, that is what it is, and if this is your streamline contours, which shows little subdued effect, you can see much more magnified effect if you plot the vorticity contours, and that is what you are seeing here. And once you notice this vorticity contour plots, you can see this thickening of the shear layer at t equal to 62, and here you can start seeing that effect of this primary bubble growing, leading to secondary and tertiary instabilities, and here you could very clearly see those vertical streaks, the eruptions, vertical eruptions, right. So, this is exactly what one would see in a computation. Let me also tell you that the Reynolds number that was based on the displacement thickness at this. So, if I look at this outflow R e delta star, that is roughly about 472. So, that means what? Inside the whole domain that we are computing, the flow is subcritical with respect to Tolman-Schlichting wave, because we know Tolman-Schlichting waves are generated at 520. So, in the whole domain, flow is supposed to be subcritical, but because of this forcing, a steady forcing, we can create a sequence of unsteady events. That is what we call as bypass transition. So, we would note this very emphatically, that the flow is fully subcritical in the computational domain, despite which we are seeing all this. And what you do is basically effect of this convecting vortex is fed through by calculating what is the induced velocity at the inflow and at the top of the domain. You do not try to calculate what is happening at the outflow. Why? Because we do not know a priori if there are some instabilities. If we say that the velocity induced here is due to the Biot-Savart interaction, then we are basically precluding all the events. So, you never do that. Most of the time at the outflow, what you do is you give boundary condition, you allow things to happen. Okay. So, we do such a thing while we fix the input disturbances at the inflow at the top of the computational domain. Okay. And that you do it by using Biot-Savart interaction. Okay. That is fairly straightforward. Now, I told you that at the outflow you do not use induced condition due to the vortex, but what you do is give a softer boundary condition, which is called here as the fully developed condition, in the sense we give the wall normal component of the velocities streamwise gradient. So, xi is along the stream direction, right. So, V itself here is like your del xi, del xi. Okay. Well, I am not writing the scale factor, there is a scale factor also involved. So, this is basically nothing but your H2V, and then when you are doing this, this is equivalent to something like this. The second derivative of psi with respect to xi equal to 0. That is what we are applying there. And we can also use the same thing in our stream function equation. What is the stream function equation? If we recall, we have this del del xi of h2 by h1 del psi del xi plus del del eta h1 by h2 del psi del eta. That is your definition of the vorticity times h1 h2. So, in this equation also you substitute this condition at the outflow, that gives you a condition on psi derivatives with respect to eta. That is what you apply there. So, that is what we are saying, that we apply the vorticity boundary condition at the outflow. So, if I know the psi, I can calculate this. From there, I can calculate the value of the vorticity at the outflow. That satisfies this fully developed condition. This is one way. The other way is to do is use Sommerfeld boundary condition. In Sommerfeld boundary condition, what we usually do is that is more aesthetically satisfying and useful also, is any condition given like this, well, any variable equal to 0, this is what we call as a fully developed boundary condition, right. What the name, the terminology signifies that the quantity under investigation is fully developed. If you move any further, it does not change anymore. That is what fully developed condition means. Whereas, there is an alternative way of looking at it, that if, as we saw, the vertical structure were moving out of the computational domain. So, it is not like as if it is fully developed there, it is a sort of a propagation phenomena. And to address that propagation phenomena, if I look at some quantity, let us say the vorticity, then I will say that it is as if it is going as a one dimensional signal, and I could give some kind of a convective velocity of that signal V c, and that is going like this. This is what is called as a Sommerfeld boundary condition. Once again, Sommerfeld proposed this, and it is used quite extensively in computation. This is called the Sommerfeld boundary condition, or some people also call it as radiative boundary condition, as if something is radiated outside. Okay. This is what you would find in many commercial software also, they basically do this. What is the problem with this case? The problem is knowing what this V c is going to be. It's not like 1D convection equation, that it's a scalar quantity that you can prescribe it up front. This is going to be something that is a part of the unknown itself, because as we saw in the probably you can see the results. Yeah, if we look at it, the last frame, if I look at it here, the vertical structure is going out. If it is going out, then what is going to happen? What you find that at different height you have different values of vorticity, and it is not necessary that it is going out like a scalar. Vorticity is a vector, it can have different orientation at each and every point, and it can go at different speed. So, this itself is going to be a function of eta, which we do not know a priori. There are many ways of handling it. One of the way that we have tried to do is calculate that velocity at the previous time step, at the whole edge. At each point you calculate this and then you let it go out. So, this is what one does in terms of computation, and these are important, these are not trivial issues, these are still a part of research topic, and we have seen that the incipient unsteady separation on the top frame that we just now saw, that we indicate as the primary instability, and of course, in subsequent frames you could note secondary and tertiary events that is essentially induced by primary instability. Of course, this goes without saying that we do not notice Tolman-Schlichting waves, and the vortices those are formed in the wall are essentially due to unsteady separation. Okay? And that is initiated by a steady convecting vortex in the free stream. This was a quite an interesting flow field. That is why, if you recall that Doligalski wrote in a review paper in 1994 that how a single convecting vortex affect a flow, that is a matter of intense research, and that was not known. We just carried it on, and we ourselves were quite satisfied because this confirms with our experimental observation. We do get the theoretical and computational verification of this, and since this is all started by a single convecting vortex, so we call it a vortex induced instability, and as you go by the definition of bypass transition of Markovin, this certainly classifies can be classified as one of the bypass transition mechanism. And we have been pretty much active in this area for quite many years now. So, we do keep investigating it in various scenarios. In the first papers, first two papers, we did look at vortex induced instability. The last paper we looked at, that is this paper in JFM, we looked at the subcritical instability on the attachment line of an infinite swept wing. So, we will talk about that. But before we do that, we need to talk about a little more about the instability mechanism. See, all the time I have explained to you the creation of adverse pressure gradient and the scouring mechanism. That is all very good qualitative description. Can we formalize it? Can we formalize it? This actually we did, and we will carry on in this discussion and we will see what happens. The experimental and the computational result clearly reveals the existence of the receptivity mechanism, right. We see the flow is receptive. That actually induces a primary and the subsequent instabilities caused by a vortex migrating in the free stream at a uniform speed. So, to understand the instability of the flow, we must understand how does the disturbance grow. And when we talk about disturbance, this is where something important happens. How do you define disturbance? Those of you who may have used some package in computing turbulent flows, you would notice that people use something called turbulence models. And one of the popular turbulence model is the K epsilon model, and the K stands for the turbulent kinetic energy and epsilon is the dissipation. So, what happens is the turbulence community per se have been looking at the turbulent kinetic energy. A breath of fresh air was actually brought in this discussion in this book by Landau and Molo Christensen. It is called Turbulence and Random Processes in Fluid Mechanics. A very nice book, very thin one, very extremely enjoyable. If one is interested about chaos and turbulence, this is a very short description of the same thing. What caught our attention was the emphasis these two authors said that if you really want to understand transition and turbulence of incompressible flow, then you better look at the total mechanical energy. Just do not simply dabble on the disturbance kinetic energy. This is a wrong way to go. Well, we were aware of some of the discussion also Markovin had made in a paper in 1991. It was a little heuristic, it was not very rigorous. Markovin suggested that what you are seeing, that all of a sudden unsteadiness appearing, that could be due to some kind of a shear noise, and that tried to look at it by looking at the Poisson equation for the pressure, static pressure. What we are intending to do here is go away from what Markovin suggested, but instead follow the lead of Landau and Mallow-Christensen, and we developed an equation for the total mechanical energy directly from Navier-Stokes equation without making any assumption whatsoever. And then we talked about this disturbance field separately from the equilibrium flow, and then tried to follow what the disturbance mechanical energy was doing. So, let us see what it is. Okay. Basically, what we can do is derive this equation 5.1 that you are seeing in front of you. How does it come about? This comes about, as I promised to you, that will appear from directly from the Navier-Stokes equation without making any assumption. So, let us see how we go about doing it. This is arrived at in the following manner. Look at it this way, that your Navier-Stokes equation is given like this. There is the local acceleration, convective acceleration that is balanced by the pressure gradient term, and then we have the viscous diffusion. Right. Now, let us write down an alternative form of this Navier-Stokes equation. Right. So, this is your Navier-Stokes equation, what we call as in the primitive variable formulation. Right. Let us write out the rotational form of Navier-Stokes equation. I will just simply write NSE to indicate Navier-Stokes. So, what we do in this trying to get this, we use this vector identity. This is a vector identity, right. So, there is no issue with that. So, if I use this over here, what am I going to get is this del V del T, and from here what is this? Del cross V is the vorticity, right. So, I could write this is V cross omega. And this term that I have here, I could put it on the right hand side. So, what I am going to get, there is already a minus sign. So, this also comes with a minus sign. So, I could write it like P by rho plus V square by 2. That is this, and then we have this term as it is. Now, this itself is your total mechanical energy. If you do not add any body force, etc., it has two components, a pressure head and the kinetic head. And this is also what you get in your Bernoulli's equation, right. In fact, from here itself one can derive the Bernoulli's equation, right. You can see how to do it. Drop this term out. Then you say flow is, let us say, irrotational, or you follow along a streamline. Then if you follow along a streamline, this term will also contribute nothing. There is a steady flow, so this goes away. So, if the spatial gradient of this quantity is 0. So, this must be constant everywhere. That is the way we come to the Bernoulli's equation. However, this is this. So, if I define this quantity itself as E, as we have done here, p by rho plus v square, I wrote v dot v by 2, that is our total mechanical energy. Now, what do? Take a divergence of this equation. So, if I take a divergence, what will happen? Del T of del dot V, it is an incompressible flow. So, that goes away. So, there is nothing that I am going to get there. On this side, then I am going to get simply del dot V cross omega, and on this side, on the right hand side, I have minus del dot del, that will be the Laplacian, right. And what about this? I am taking again a divergence. So, that could simply just go away. So, we will not get this. So, what we have is essentially this. So, del square E is equal to del dot V cross omega. Just simply use again some vector identity, del dot A cross B, and you can write it down, you get this equation. So, you can see what is going to happen now is, so this is a very straightforward equation that we have is del square E is nothing but del dot V cross omega, and that we can simplify again using the incompressible flow assumption. There will be many terms, 4 terms, 2 terms will drop out, and we will have only 2 terms left behind. That will find del cross V dot omega and minus V dot del cross omega. So, this itself is again omega dot omega minus V dot del cross omega. So, that is your equation 3.51. Okay? That is how we can derive it. Now, this is your for the total field. What we could do is, of course, we could simplify it a little further. What you are noticing is this path. What is E? E is something like your irrotational part. You know, it is the energy. It's got nothing to do with like a rotational aspect of it. Whereas, on the right hand side, it is driven by the rotationality of the flow. This is how the vorticity field interacts with itself, and of course, how the velocity and the vorticity field interacts. Right? That is what we are looking at. That the instability is related to the rotationality of the flow, and the instability is driven by the right hand side. How the energy is going to, whether it is going to grow or decay, depends on what this right hand side is doing. Now, what you could do is you could again appeal to the giants. Sommerfeld, in writing a book on partial differential equation in 1949, he talked about the properties of Poisson equation in the context of heat transfer. He said that if I write the Poisson equation for the temperature field, then in the right hand side, if the right hand side quantity is positive, it is going to be a sink of heat, and if the right hand side is negative, then it is a source of heat. So, we are anyway talking about energy. So, we can draw the analogy and look at the right hand side, what the right hand side is doing, because that is what is driving, that is what we made the comment, that what you are looking at is del square E, the distribution of E, the boundary value problem is determined by the forcing on the right hand side. So, basically then we can follow the evolution of E by just simply looking at what this right hand side is doing with time. However, we are interested not only on the total mechanical energy, but we want to find out how the disturbance energy is growing. So, what I could do is I could split the total energy in terms of a mean path plus a disturbance. I could do that, isn't it? And once I do that and I substitute it here, then on the left hand side, of course, I am going to get del square E m plus epsilon E d. That is that, and on this side what am I going to get? This is going to be omega m, write it lowercase, epsilon omega d dot the same thing. That is the first part, and the same way I could split the velocity field also into mean and a disturbance. Right. So, this is the equation. Now, of course, order 1 quantity should balance with order 1 quantity. So, if I remove all the order 1 quantity, what am I going to get on the left hand side? Well, I have this, the order epsilon quantity on the left hand side. What about here? Omega m dot omega m, that was the mean part, that is gone. So, we do not worry. Omega m will interact with this, that will be one set of term. So, that I will get omega m dot omega d, right. What about this? This into this also will give me the same thing. So, I get twice of that. In addition, I am just simply for the sake of writing, not leaving out anything, this is the order epsilon square term, how the disturbance field interacts with itself, that is also there. And what about here? The mean part will go away with the V m dot del cross omega m. So, that we do not worry about. We look at this part, that will give us epsilon V m dot del cross omega d. This is this into this. Now, this into this also I will get epsilon V d dot del cross omega m. That is this part, and then of course, we will also have the quadratic nonlinearity, that will be this. So, what you are noticing, of course, you can drop out all the epsilons, and then you are going to get this term. So, we will write here 2 omega m omega d, there would be this term, right, and these go away and this. So, what you see as the equation 2 there, 5.2 has all the terms. Only thing is we did not write these as order epsilons, but that is implied. This term is a lower order quantity, so is this term, right. So, if we want to be consistent, we could drop this out, and that will be your corresponding linear analysis, right. This is how we perform linear analysis. So, basically this is the thing. What you are noticing though that the disturbance energy is dictated upon how the mean vorticity interacts with the disturbance vorticity, right. So, in the case of our numerical and experimental investigation, we already have a mean flow vorticity distribution, that is the boundary layer vorticity, right. With the boundary layer I can have a vorticity distribution, and now over and above this disturbance vorticity omega d is going past, it has its footprint there, that is interacting there. That is one of the sort of a player in dictating what happens, and we have seen it depends on the sign. What we have said that if I have a flat plate, I have vorticity of one sign, and then if the vorticity is positive, then I get something that would give me a dominant quantity from here. If that dominant quantity happens to be a negative quantity, then we will have a source of disturbance energy. So, now you can see how this whole thing comes about. This is the primary term, look at this, this is a lower order term. To begin with, in the primary stage, this could be suppressed, not thought about important. It would come into play once you are looking at secondary and tertiary instabilities. Okay. Okay. So, this equation, as you are noticing here, brings out certain features that we said that how the mean and the disturbance vorticity field interacts with each other, that would probably determine your the onset itself, the primary instability that we talk about. So, to really make use of this equation, what we need to know is what is our equilibrium flow or the mean flow. Mean does not necessarily mean that we are looking at only a steady flow. It could be an unsteady flow. That is what we are saying, that once you have the wherewithal of describing what your equilibrium flow is, whether it is steady or unsteady, you can use this equation to study its stability or instability. Do you see the quantum leap from what we have done with the Orson field equation? We needed a steady flow, we needed to make it parallel, and all kinds of assumptions limited our visibility. Here we are not saying that. We are ready now even to study the instability of an unsteady flow, mean flow. That is what is pointed out here. We can study both steady and unsteady flows, does not restrict us. And this equation is very, very generic, because we started off from Navier-Stokes equation. We did not make boundary layer assumption, we did not make parallel flow assumption, we did not talk about linearity, none of this thing have come about. So, this is the most generic thing that could have happened, and if it is indeed so, then I should be able to get what others have gotten with those limited approximations, right. How you get Tolman-Schlichting, that should be also buried in this information, and indeed we did show it in a paper in physics of fluid and a paper in physical review letters, that you could actually make use of this equation and explain the occurrence of Tolman-Schlichting waves too, and that has been done, thankfully. So, now we have really scanned the whole horizon, and then we can show that Orson field equation information is also embedded in this equation set. Now, if we look at the computational data, we know the flow was evolving with time, but in the initial stage, when the vorticity was very much upstream ahead of the flat plate, then the flow was not changing with time. So, if we take one such snapshot as our representative mean flow, undisturbed flow, that is subsequently perturbed by the convecting vortex, then we can make use of this. What we can do is we can calculate the disturbance quantity, because when we are solving the Navier-Stokes equation, we are solving for the whole quantity. We are not solving for mean separately or disturbance quantity. So, what we have is the total field. Now, if I now identify a so called equilibrium flow, which is let us say the solution at t equal to 0, then from the instantaneous solution I can subtract that, that will be my imposed disturbance, right. So, that is this. The disturbance quantities at any time would be obtained by subtracting the mean flow from the instantaneous solution of the Navier-Stokes equation. It is as simple as that. Now, with the help of the mean and disturbance quantity, I could really compute the right hand side of that disturbance energy equation that we have written here. What we did, what we continue to do is not worry about solving this Poisson equation, which you can always do. But what we would rather like to do is get a qualitative understanding of the ensuing instability by working out the right hand side. So, if I am solving the stream function vorticity field equation, I have omega m plus omega d. From there I can split them out. I have the velocity field from the stream function equation, that also I can split it into V m and V, and then I can work out the right hand side. Once I have the right hand side, I know, using that Sommerfeld's idea, looking at the sign of the right hand side, I could say where the disturbance energy sources are, or where it is working as a sink. That is interesting. Now, this is what we have plotted here. We calculate the right hand side and we do a contour plot. What is the legend about this plot? The blue, darker blue shade imply the sources of energy. So, those are the streaks along which you get negative values. And what you notice that this is the leading edge of the plate. Okay. So, leading edge of the plate is one location where you see disturbance sources getting created. However, you also notice that what is being created at the leading edge does not come inside, they kind of stay outside the shear layer. This is more or less the edge of the shear layer. So, it remains outside. So, the leading edge point, it is quite well known for a long time that that has some role to play in flow instability, and that is what we are also seeing. Well, it does have, but it stays outside. Also, we have a second site which is about 20 delta star from the leading edge. That is where I see another more intense source of disturbance energy. And as I told you, this calculation is all for subcritical domain, because the RE delta star here is 472. So, despite that, we are seeing that convecting vortices creates all kinds of disturbance quantities, which leads to an interaction given by the right hand side, and that shows two sides of instabilities. And of course, there is one vorticity field, there is another vorticity field, they can interact also. And you start noticing that thing is happening. There is an interaction between these two disturbance sources, one starting from the leading edge, another is somewhere in the middle of the domain. And we did talk about those vertical eruptions. You can see those are responsible for linking these two sources. Those vertical eruptions actually build a bridge, and you notice what it does. This is a discrete event, but once this discrete event is created, it creates a link, and then the one here actually lifts off, and this seems to be inhibited, but this is what you are going to see, a sequence of instabilities happening like this. So, as if the leading edge disturbance seems to feed energy here, and that basically reinforces the disturbances that are there on the flat plate. So, one thing that we realize that in studying a flow field of this kind, if we are doing the computing, you have no choice but to take the leading edge. There are many people who have tried to compute the flow by excluding the leading edge. If you exclude the leading edge, you are not going to pick this up. Okay? So, this is rather very crucial. That was the reason that we computed the flow field including the leading edge. So, we can make the following observations, that at early times we know two sites from where instability originates. They are at the leading edge of the plate and a location more than 20 delta star from the leading edge of the plate. This we have noticed. We also noticed that the leading edge instability is weaker and the disturbance energy sources are active only outside due to this weak instability. And what happens is the other site that grows in the interior of the shear layer is stronger, and that gets stronger with time. A little before this time, we saw those snapshots at 62, 82 and so on and so forth. So, a little before 80, we start seeing an eruption coming out from the wall and hits those upper deck of the disturbance. That is what we have called as the vertical eruptions. Once that does, that creates a kind of a bridge between these two disturbance sources. This is exactly what people have talked about in fully developed turbulent flow also. During the burst sequence of fully developed turbulent flow, people do see some kind of a vertical eruptions, and that is the bridge between the two energy sources via the eruption, and this creates a kind of a spike. Remember, we talked about Brinkman-Walker's investigation in the cross flow plane of a fully developed turbulent flow. So, what we are seeing here in the streamwise direction, we can do a sort of a isolated analysis on the cross flow plane, and there also we will see some spikes forming. So, you do see this kind of things in fully developed turbulent flow. I just would like to emphasize upon all of you that why we did not study the turbulence the way people study turbulence, because what you see in fully developed turbulent flow, it is in the genesis, how it all originated. So, that is why it is much more productive that you try to take a composite picture of the whole thing by starting off from the primary instability all the way down, and that is what we are also talking here, that even while we are studying instabilities, we can see some of those elements which people have found out by simply focusing upon turbulent flow itself. But this kind of a controlled experiment, the controlled numerical simulations does yield a tremendous dividend, and we should be keeping this thing in mind. And you have already seen in those stream function and the vorticity contour plots, the spikes were noted, and we did note those spikes were nothing but your secondary and tertiary instabilities. Okay. And we also noticed that the visualized instability shows the disturbance energy sources interact with each other downstream, which actually determines the asymptotic state. So, what we are going to see far downstream, that information is built in this initial interaction itself. That is what I say, that it is always necessary that we must include the leading edge in computing unstable or transitional flows. Otherwise, what will happen? See, the top disturbance source was kind of creating a shield. It was trying to shield the inviscid flow outside with this viscous flow inside. So, if I do not take that leading edge, then I will just simply get those unimpeded spike stage. This has been done by those couple of papers that we talked about in the last class also, Perridier, Smith and Walker. They did write couple of papers in JFM, and they did see that this spike goes heavenwards, and their actually computations broke down. So, they concluded from that if there are elements of vertical eruptions, those eventually leads to turbulence. But they are on the conservative side, because they do not see the moderation due to the presence of the leading edge, and their breakdown is rather spectacular. There was also a computation done by Bobko and Castle later, had the same issue of not including the leading edge. We must also point out another aspect of the present energy based instability theory, that if I look at this equation, this is like a forced vibration problem, right. What is the quantity of interest? Is E d, that is forced by the right hand side. Okay. So, if I am trying to look at the transfer function, what should I look at? I should look at it without the excitation. That means, I should look at it without the right hand side. So, basically I will be looking at a Laplacian of E d as the transfer function of this disturbance energy. And what you notice that nobody has really reported from a Laplacian operator that it can lead to some kind of a seed for instability. So, by itself intrinsically this is not unstable. Until unless you have the forcing on the right hand side, nothing would happen, because the governing equation for E d is del square E d equal to 0. That is the point we are making here. The vortex induced instability is completely driven by interaction of velocity and vorticity field. So, basically what we are noticing is the rotationality forcing the issue through the right hand side to determine what happens to a scalar quantity like an energy. See, this is different from what Markovin conjectured. Markovin did not talk about this kind of equation. He was talking about a Poisson equation for the static pressure, and he had lots of term on the right hand side, and he called those as a shear noise term. But this is a complete consistent picture. Okay. So, this is something. What is more, I do not know whether you have noted the issue or not, that the main issue is really how energy is exchanged initially between the mean and the disturbance field. This is clearly brought out by this term and this term. Okay. So, how the mean is reacting with the disturbance field, that is what you are getting here. It is also noted that during the later stages of bypass transition, large coherent vortices are formed inside the shear layer. We saw those, what we call as unsteady separation or the vertical eruptions. They are coherent vortices, right. They are the coherent vortices. People have been looking at it for a long time in turbulent flows. Okay. So, we basically would look at those coherent structure using proper orthogonal decomposition later in this course. We will talk about it in the next class. Okay. We will begin from here.